In this video, I'm continuing on our discussion of the cause of the radiation reaction. And we got to the point where we had written out the self-interaction term, or the force, basically of charge 1 acting on charge 2, where charge 1 and charge 2 are the two pieces of our point charge. And we eventually want to now take this expression and let the variable d, written right here, that's the separation of the two charges, and we want to let that go to 0. So essentially, just to recap, we have two charges separated by d, and eventually we're going to let d go to 0 and give us our point charge, Q. Okay, and so to kind of investigate this further, we're looking at, say, a Taylor expansion in position, and we're now down to the point where we have this length L, which is the length that the charge distribution has moved as a function of the time difference, capital T. So the time difference, capital T, is the time between the initial time, tr, and the time which we actually measure anything, t. Okay, so when we get back to it, we now have our expression, and this expression now is L, this length, in terms of the time difference. Okay, so now what I want to do is to look at the distance d, which we can write out as ct squared. So the distance that the information or the fields would travel, ct minus L squared. Okay, so now if we put this in, we essentially have that ct squared is equal to L squared plus D squared. And again, refer to the previous lecture about what these variables are. So when I do that, I now have D is CT quantity squared minus L squared, and L squared we said was 1/2 the acceleration times the time difference squared plus 1/6 the derivative of the acceleration times the time difference cubed plus ... That is squared, and then this whole thing, I take the square root. So we want to get the distance d, the gap between the two charges, in terms of time. Okay, so anyway, so I can factor out a ct. So d is now equal to ct 1 minus a over t 2c plus a dot t squared 6c plus ... squared square root right there. Okay, and now we can use the binomial expansion to write this out as ct times 1 minus okay, I'm sorry. So we want to write this out as ct. So we take the binomial expansion of this right here, and we get ct, and then we multiply by ct. So we get ct minus a squared t cubed over 8c plus something in parentheses times t to the fourth plus ... Okay, so essentially what we did is we multiplied out the expression that's squared in the parentheses, and then took the binomial expansion of the square root, and we get something like this. Okay. Now, now what we would want to do is we want to write the time as a function of d. So to first order, if we just ignore all of the higher order terms like the t cubed and the t to the fourth, then d is approximately ct. So if we include just the second order term, then d would be approximately ct minus a squared over 8c d over c cubed. So what we kind of did is a little bit of a trick where we took this expression here and plugged it in up here. Okay, just to get rid of that. So anyway, so this is just our model. Just remember that. Everything is based on assumptions. So anyway, so I could write this out as ct minus a squared d cubed over 8 times c to the fourth power. And so therefore t is d over c plus a squared d cubed over 8c to the fifth power. Okay, so now if we take that and plug that back into our expression for L, L becomes 1/2 a d over c plus a squared over 8c to the fifth d third plus a d to the fourth term dot dot dot, all of that squared, plus 1/6 the derivative of the acceleration d over c plus a squared over 8c to the fifth d to the third plus d to the fourth power term, all of that cubed, because we're basically putting everything now into our Taylor expansion from before, and then plus dot dot dot. Okay. Okay, so now what we can do is we could eventually multiply out the parentheses. So we could square the first parentheses. We could take the cube of the second parentheses. We can group together terms. And so you're just going to have to go along with me on this and say that it's L is now 1/2 a d squared over c squared plus a dot 6c cubed d cubed plus d to the fourth terms plus dot dot dot. Okay, so now if we were to put that back into our equation for the force, self-interaction is q squared over 4 pi epsilon naught minus a over 4c squared d plus a dot 12c cubed plus dot 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 dot. Oh, I'm sorry. Plus a term that depends on d plus dot dot dot, which would then be like d squared, d cubed. So we're basically going from a 1 over d to a d to the 0 to, so this is the d to the minus 1 term, d to the 0, d squared, all things like that. Okay. So if you remember that the accelerations are written in terms of the initial time, like so, then I could do an expansion of the accelerations. Where now I'm expanding it around the time of now. So I get a minus sign because this is essentially minus t. So that's plus dot dot dot. And so this equals a t minus a t d over c, like so. So when I put those into the expressions, I now get, for the force, q squared over 4 pi epsilon naught minus a t, not a tr, 4 over c squared d plus a dot of t, 3 c cubed plus a term in d plus dot dot dot. So again, this is the d to the minus 1 term, d to the 0 term, d to the 1, d to the 2, so forth and so on. Okay, so the first term is in the acceleration. So this is Newton's second law, right here. Okay. So what that means now is Newton's second law, but the mass is now rewritten as 2 times mass 0 plus 1 over 4 pi epsilon naught q squared over 4dc squared, like so, where this is what we're going to call the rest mass. So the mass, if there was no motion whatsoever in the charges, it would be m0. But the fact that we have moving charges means it has now modified the mass. The second term in the expression, right here, is the radiation term, because it has a derivative of the acceleration. So I'm going to write this as frad int, and that is mu0 q squared a dot over 12 pi c, where we've used epsilon naught c squared to equal 1 over mu0 in order to get that expression. But we now have an expression for the radiation term in this one particular toy model that we've created. So if you look at this, we are actually very close to the Abraham-Lorentz equation and we're only off by a factor of 2. Okay, so even in this toy model, we use dumbbells instead of a sphere. You're only off by this factor of 2. And this is because we've only considered half of the problem of the interaction between Q1 and Q2. And so that's why I put the int label right here on that. Is we're only looking at the interaction, the kind of the internal interaction, and so the force on itself gives the other factor. So in the end, if we were to include a factor of 2, then we would get our force for the radiation would be mu0 q squared a dot over 6 pi c. So that's the Abraham-Lorentz equation. But what hopefully through this whole derivation, which I don't want you to necessarily follow all the steps in great detail, but what we've discovered is that this dampening force due to radiation is due to internal forces in the charge distribution. And so that leads to the greater question of, can we really have a point charge, or does there have to be some spatial aspect to every charge?